Hello, my name is Sarah Takim, and in today's video, we will be looking at skip lists, specifically the skip list visualizer. Now, before we begin, let's ask ourselves some key questions. This is what a skip list looks like. It is important to see what they are before you fully understand how they work. Skip lists are a probabilistic data structure that allows O log n search complexity. They were invented in 1990 by the computer scientist Will Pugh. As previously mentioned, the search time of skip lists is O log n. The structure of skip lists is randomized. Commonly, coin flips are used to build and determine the shape of the data structure. They are called skip lists due to the ability of skipping over items when searching. How do we make a skip list? We have the option to insert or delete keys. However, you can only delete keys if there are any items in the list. There are O log n levels in a skip list. These levels begin with negative infinity and end with positive infinity. They are also known as the header and sentinel nodes. Each level below another has twice the amount of elements due to the even likelihood of heads versus tails. Now, let's discuss insertion with a skip list. Firstly, we will insert an element by comparing the key of the next node to the current node which we are trying to insert. If the key of the next node is less than the key that is to be inserted, we will move on to the next node in the same level. If the key on the next node is greater than the key that is to be inserted, we will store the pointer to the current node and move one level down and continue the search. At the last level, we will place the key, depending on the surrounding elements. Each new element that is inserted should be placed to the lowermost level. Half of the new elements should advance to the next level for balance and structure. When inserting an element, we want to flip a fair coin. If the coin lands to heads, we will add the element to the next level and keep flipping until you receive a tails. This method guarantees that the skip list is approximately evenly distributed. Now we can cover deletion, which is a bit simpler than insertion. When you delete an element, it is very similar to element lookup. If the key of the next node is less than the search key, you keep progressing on the same level. However, if the key of the next node is greater than the key that will be deleted, you want to store the pointer to the current node and move down one level to continue the search. Once the element that is to be deleted has found, we must rearrange the stored reference values. The rightmost element's new reference value is the key that was once to the left of the deleted element, and vice versa. Now, we are going to create a skip list and discuss some of the key steps that we will be taking to create this skip list. Step 1. We will insert the element 20, and we will assign the coin flips to 110. This means that the value inserted will be placed onto the two lists above the bottom list, as we see right now in the demonstration. Step 2, we will now insert the element 40, and we will not be assigning coin flips and let the computer randomly decide. So we see that it places 40 on 5 lines on top of the bottom list. So the coin flip resulted in heads 5 different times. So now we can insert 10. So starting at negative infinity, we see that 20 is greater than 10, so the pointer moves down for each row and places 10 in front of the 20, as 10 is less than 20. So now we can insert 20 once more. And here we'll see that it really does nothing, as 20 is already in our list. Now we can insert 5. So now for 5, the visualization is doing something very similar to what it did when we inserted 10. Now we can insert 80. Now let's remove 20 from the skip list. So we see that the skip list shrinks a bit when the column of the 20s is removed. So now we can insert 100. Now the 100 will be the greatest value in our skip list, so it will be the closest to positive infinity. Now we're going to insert 20 using coin flips of 1, 0. So we know that the value 20 extends past the negative infinity, 5, and 10, as they're all less in value. So it stops at the 10 and then goes down all the rows as positive infinity is greater than 20. So the value is placed on the bottom row and then the row above it because the coin flips resulted in one head, as we see right here. Now we're going to insert 30. Now we will delete 5 from the list. So it's searching for values less than 5, and then going down through the negative infinity, it finds a 5, and now we'll remove the 5. Now we can insert 50. And now we can look up 80. Now it's going through all of the values at the top in each list and moving right every time there is a value greater than 80, and it has found 80. Now we have finalized our skip list, and this is our finished skip list. Now here we can see our finalized skip list. The skip lists start with and end with negative infinity and positive infinity, respectively. The elements in every row are sorted properly. The skip list has been finished and was sorted. Now let's answer the question, are skip lists efficient? And the short answer is yes. Why and how are they sufficient? Because of the probabilistic feature, the coin flip, performance of the skip list is enhanced. The skip lists perform well on rapid insertions due to the fact that it doesn't perform any rotations or reallocations. The implementation is overall simpler than its counterparts, such as the self-balancing binary tree or linked lists. It is also faster than the linked list because of the runtime of linked lists being theta n. Now, we know that skip lists are very efficient and we know how they work. Thank you for listening to my lecture on skip lists. I hope you enjoyed.